The Universal Product Code is a barcode symbology that is widely used in the United States, Canada, the United Kingdom, Australia, New Zealand and in other countries for tracking trade items in stores. Its most common form, the UPC-A, consists of 12 numerical digits, which are uniquely assigned to each trade item. Along with the related EAN barcode, the UPC is the barcode mainly used for scanning of trade items at the point of sale, per GS1 specifications. UPC data structures are a component of GTINs. All of these data structures follow the global GS1 specification, which bases on international standards. Some retailers do not use the GS1 system. Other retailers use the EAN UPC barcode symbology but without using a GTIN. Composition: each UPC-A barcode consists of a scannable strip of black bars and white spaces, above a sequence of 12 numerical digits. No letters, characters, or other content of any kind may appear on a standard UPC-A barcode. The digits and bars maintain a one-to-one correspondence, in other words, there is only one way to represent each 12-digit number visually, and there is only one way to represent each visual barcode numerically. The scannable area of every UPC-A barcode follows the pattern SLLLLLMRRRRRE, where the S, M, and E guard bars are represented exactly the same on every UPC, and the L and A sections collectively represent the 12 numerical digits that make each UPC unique. The first digit L indicates a particular number system to be used by the following digits. The last digit R is an error-detecting check digit that allows some errors in scanning or manual entry to be detected. The non-numerical identifiers, the guard bars, separate the two groups of 6 digits and establish the timing. Note: UPC-A 123,456,789,999 corresponds with UPC-E 234,569. Equivalent UPC-A and UPC-E barcodes share the same check digit, which is 9 in this case. Formatting: UPC-A barcodes can be printed at various densities to accommodate a variety of printing and scanning processes. The significant dimensional parameter is called X dimension, the ideal width of single module element. A single X dimension must be used uniformly within a given UPC-A barcode. The width of each bar and space is determined by multiplying the X dimension by the module width of each bar or space. Visually, a grouping of 2 or more adjacent bars appears a single wide bar, while a grouping of 2 or more adjacent spaces appears a single wide space. Since the guard bars each include 2 bars, and each of the 12 digits of the UPC-A barcode consists of 2 bars and 2 spaces, all UPC-A barcodes consist of exactly a plus A, 12AA, A2, A equals A30 bars, of which 24 represent numerical digits and 6 represent guard bars. The X dimension for the UPC-A at the nominal size is 0.33 ohm. Nominal symbol height for UPC-A is 25.9 ohm. In UPC-A, the dark bars forming the start, middle, and end guard bars are extended downwards by 5 times X dimension, with a resulting nominal symbol of height of 27.55 ohm. This also applies to the bars of the first and the last symbol characters of UPC-A symbol. UPC-A can be reduced or magnified anywhere from 80% to 200%. A quiet zone, with a width of at least 9 times the X dimension, must be present on each side of the scannable area of the UPC-A barcode. UPC-E requires 9 X dimension units on the left side and 7 on the right. For a GTIN 12 number encoded in a UPC-A barcode symbol, the first and last digits are always placed outside the symbol to indicate the quiet zones that are necessary for barcode scanners to work properly. Encoding: the UPC-A barcode is an optical pattern of bars and spaces that format and encode the UPC digit string. Each digit is represented by a unique pattern of 2 bars and 2 spaces. The bars and spaces are variable width. They may be 1, 2, 3, or 4 units wide. The total width for a digit is always 7 modules. To represent the 12 digits of the UPC-A code requires a total of 7 A, 12A equals A 84 modules. A complete UPC-A includes 95 modules, the 84 modules for the digits combined with 11 modules for the start, middle, and end patterns. The S and E patterns are 3 modules wide and use the pattern bar space bar. Each bar and space is 1 module wide. The M pattern is 5 modules wide and uses the pattern space bar space bar space. Each bar and space is 1 module wide. In addition, a UPC symbol requires a quiet zone before the S pattern and another quiet zone after the E pattern. Each digit is 7 modules wide. The UPC's left side digits have odd parity, which means the total width of the black bars is an odd number of modules. The right-hand side digits have even parity. Consequently, a UPC scanner can determine whether it is scanning a symbol from left to right or from right to left. After seeing a start or end pattern, the scanner will first see odd parity digits if scanning left to right or even parity digits if scanning right to left. With the parity direction information, an upside-down symbol will not confuse the scanner. When confronted with an upside-down symbol, the scanner may simply ignore it or the scanner may recognize the digits and put them in the right order. There is further structure in the digit encoding. The right-hand digits are the optical complement of the left-hand digits. That means that black bars are turned into white spaces and vice versa. Numbers on the right side of the middle guard bars are optically the inverse of the numbers to the left. In other words, while a number on the left side of the UPC will be made up of black bars and white spaces, the same number on the right side would be made up of white bars and black spaces. For example, the left-hand 4-digit is spacer, 1, bar, 1, spacer, 3, bar, 2. The right-hand 4-digit is bar, 1, spacer, 1, bar, 3, spacer, 2. Numbering, UPC-A and UPC-E each provide a theoretical maximum of 1 trillion unique barcodes, though in practice the number of barcodes is limited by the standards used to create them. For instance, the last digit is the check digit and therefore can only be one correct value for UPC-A. This gives only 100 billion possibilities. UPC-A, A, equals 1 million A, 1 million equals 1 trillion. UPC-E, 10 possible values per digit A, 2 possible parities per digit equals 20 permutations per digit 6 digits equals 64 million. Number system, the first digit indicates the number system to be used for the subsequent digits. The following number system digits and their numbering schemes are 0, 1, 6, 7, 8, for most products. The LLLLL digits are the manufacturer code, and the RRRRR digits are the product code. 2, reserved for local use, for items sold by variable weight. Variable weight items, such as meats and fresh fruits and vegetables, are assigned a UPC by the store, if they are packaged there. In this case, the LLLLL is the item number, and the RRRRR is either the weight or the price, with the first are determining which. 3. Drugs by national drug code number. Pharmaceuticals in the U.S. have the remainder of the UPC as their national drug code number. Though usually only over-the-counter drugs are scanned at point of sale, and DC-based UPCs are used on prescription drug packages and surgical products and, in this case, are commonly called UPN codes. 4. Reserved for local use, often for loyalty cards or store coupons. 5. 9. Coupons. The manufacturer code is the LLLLL, the first 3 are a family code, and the next 2 are a coupon code. This 2-digit code determines the amount of the discount, according to a table set by the GS1 US, with the final A being the check digit. These coupons can be doubled or tripled. Check digits. In the UPC-A system, the check digit is calculated as follows: add the digits in the odd-numbered positions together and multiply by 3. Add the digits in the even-numbered positions to the result. Find the result modulo 10. If the result is not 0, subtract the result from 10. For example, in a UPC-A barcode 036000291145X, where X is the unknown check digit, X can be calculated by adding the odd-numbered digits, multiplying by 3, adding the even number digits equals 58, calculating modulo 10, subtracting from 10. The check digit is thus 2. This should not be confused with the numeral x, which stands for a value of 10 in modulo 11, commonly seen in the ISBN check digit. Variations: UPC in its most common usage technically refers to UPC-A. Other variants of the UPC exist. UPC-E, to allow the use of UPC barcodes on smaller packages where a full 12-digit barcode may not fit. A zero-suppressed version of UPC was developed called UPC-E, in which the number system digit and all trailing zeros in the manufacturer code and all leading zeros in the product code are suppressed. This symbology differs from UPC-A in that it only uses a 6-digit code, does not use middle guard bars, and the n-bit pattern becomes 010101. The way in which a 6-digit UPC-E relates to a 12-digit UPC-A is determined by the last digit. It can only be used with UPC-A number system 0 or 1, the value of which, along with the check digit, determines the parity pattern of the encoding. With the manufacturer code represented by X's, and product code by N's then, for example a UPC-E barcode with the number 654,321 would expand to the UPC-A 065100004327 or 165,100,004,327, depending on the parity pattern of the encoded digits, as described next. UPC check digits are calculated using this expanded string in the same way as used by UPC-A. The resulting check digit is not added to the barcode, however, but is encoded by manipulating the parity of the 6 digits which are present in the UPC-E, as shown in the following tables. Our example code 654,321, therefore, would become 1-1-1-1-1-2-3-1-1-1-2-3-2-1-2-1-2-1-2-1-2-1-1-1-1-1. The resulting barcode would look roughly like this. Note: the UPC can detect 100% of single-digit errors and 89% of transposition errors. EAN. The EAN was developed as a superset of UPC, adding an extra digit to the beginning of every UPC number. This expanded the number of unique values theoretically possible by 10 times, from 1 trillion to 10 trillion. EAN 13 barcodes also indicate the country in which the company that sells the product is based. The leading digits of the code determine this, according to the GS1 country codes. The EAN 13 encoding rules encode the leading 13th digit by modifying the encoding of the left-hand half of the barcode. The original rules for UPC are treated as a 0 if read as EAN 13. A UPC barcode XXXXXXXXXXXXXX therefore is the EAN 13 barcode OXXXXXXXXXXXXXX. It is possible to prefix a UPC barcode with a 0. They become EAN 13 rather than UPC-A. This does not change the check digit. All point-of-sale systems can now understand both equally. EAN 8 is an 8-digit variation of the EAN number. UPC Usage Notes: currently all products marked with an EAN will be accepted in North America in addition to those products already marked with a UPC. Any product with an existing UPC does not have to be remarked with an EAN. In North America the EAN adds 40% more codes, mainly by adding 10 through 13 feet to the 00 through 09 already in use. This is a powerful incentive to phase out the UPC. Other variations: UPC-B is a 12-digit version of UPC with no check digit, developed for the National Drug Code and National Health-Related Items Code. UPC-C is a 12-digit code with a check digit. UPC-D is a variable length code with the 12th digit being the check digit. These versions are not in common use. UPC-2 is a 2-digit supplement to the UPC used to indicate the addition of a magazine or periodical. UPC-5 is a 5-digit supplement to the UPC used to indicate suggested retail price for books. As the UPC becomes technologically obsolete, It is expected that UPC-B and UPC-C will disappear from common use by the 2010s. The UPC-D standard may be modified into EAN 2.0 or be phased out entirely. History: Wallace Flint proposed an automated checkout system in 1932 using punched cards. Bernard Silver and Norman Joseph Woodland developed a bullseye-style code and patented it. In the 1960s, railroads experimented with a multi-color barcode for tracking rail cars, but they eventually abandoned it. A group of grocery industry trade associations formed the Uniform Grocery Product Code Council, which with consultants Larry Russell and Tom Wilson of McKinsey & Company, defined the numerical format of the Uniform Product Code. Technology firms including Shergan, IBM, Litton Zellweger, Pitney Bowes Alpex, Plessey Anchor, RCA, Scanner Incorporated, Singer, and IMO Industries Data General proposed alternative symbol representations to the Council. In the end, a symbol selection committee chose to slightly modify, changing the font in the human-readable area, the IBM proposal designed by George J. Lehrer. The first UPC-marked item ever scanned at a retail checkout was at the Marsh Supermarket in Troy, Ohio at 8:01 a.m. on June 26, 1974, and was a 10-pack of Wrigley's Juicy Fruit chewing gum. The shopper was Clyde Dawson and cashier Sharon Buchanan made the first UPC scan. The NCR cash register rang up 67 cents. The entire shopping cart also had barcoded items in it, but the gum was merely the first one picked up. This item went on display at the Smithsonian Institution's National Museum of American History in Washington, D.C. IBM proposal: around late 1969, IBM at Research Triangle Park in North Carolina assigned George Lehrer to develop a supermarket scanner and label. Late 1970 Herb Baumeister provided equations to calculate characters per inch achievable by two IBM barcodes, Delta A and Delta B. In February 1971, Baumeister joined Lehrer. Mid-1971 William Krause invented a new barcode called Delta C. It achieved 4 times the characters per inch as Delta B. Delta B compared bar widths to space width to code bits. This was extremely sensitive to ink spread, where too much ink or pressure would cause both edges of a bar to spread outward and too little to cause them to shrink. To make it worse, as bars spread, spaces shrink and vice versa. Delta C achieved its higher performance by only using leading to leading or trailing to trailing edges, which was unaffected by uniform ink spread. The code provided best performance when it had a defined character set with a fixed reference distance that spanned most or preferably all the character. August 1971 Krause joined the scanner effort. After several months they had made no progress. They were aware of the RCA Buller unregistered trademark SI label that could be scanned with a simple straight-line laser scanner, but a readable label was far too large. Although Litton Industries proposed a Buller unregistered trademark SI symbol cut in half to reduce the area, it was still too large and presented the same ink smear printing problems as the RCA symbol. The redundancy and checking ability were removed completely. They were also aware of the many proposals from around the world, none of which were feasible. In the spring of 1972 Baumeister announced a breakthrough. He proposed a label with bars that were slightly longer than the distance across all bars that needed to be read in a single pass. This label could be scanned with a simple OEXA scanner, only slightly more complex than the straight-line laser scanner. The next day Baumeister suggested if the label was split into 2 halves, the bar lengths could be cut nearly in half. These 2 proposals reduced the area from the Buller unregistered trademark SI by 1/3 and then 1/6. The image to the right showed the label proposed by Baumeister. He did not specify any specific barcode, as that was well understood. Except for the barcoding and 10 digits, the UPC label today is his proposal. Shortly after that Baumeister transferred to another area of RTP. Lehrer proceeded to define the details of the label and write a proposal. Joe Woodland was assigned as planner for the project and aided Lehrer with writing his proposal. Woodland was the official inventor of a non-specific printed barcode in the 1940s and had also been involved in the RCA Buller unregistered trademark SI scanner. Laura Euro unregistered trademark S first attempt with a barcode used delta B. The resulting label size was about 6 inches by 3 inches, which was too large. Krause suggested that Laura use his delta C barcode and provided a copy of his patent that had a sample alphanumeric character set and rules to generate other size alphabets. This reduced the label size to about 1.5 euro x 0.9 euro. Later Laura asked Krause for assistance in how the scanner could detect a label. Together they defined guard bars and a definition of how to detect the label. The guard bars also provided identification for half-label discrimination and training bars for the scanner threshold circuits. Laura had a complete label definition and proceeded to write his proposal. Previously Krause had an idea for a simple wand worn like a ring and bracelet. He decided to develop that wand to provide a demonstration of the label. On December 1, 1972, IBM presented Laura's proposal to the Supermarket Committee in Rochester, Minnesota, the location where IBM would develop the scanner. During the presentation, Krause gave a lab demonstration where he read UPC-like labels with his ring wand. In addition to reading regular labels, he read the large 2-page centerfold label in the proposal booklet. He then turned to a page showing a photo of labeled items sitting on a table. The labels were small and flawed due to the resolution of the printed photo, but the wand read many of them. This demonstration showed the robustness of the pure Delta C code. The proposal was accepted. 1 month later, January 1, 1973, Krause transferred back to Advanced Technology and Laura remained with the full responsibility for the label. Dymo Industries, makers of handheld printing devices, insisted that the code be character independent, so that handheld printing devices could produce the barcode in store if the items were not barcoded by the manufacturers. Dymo's proposal was accepted by IBM and incorporated in IBM's latest proposal. It was decided that the two halves of the label should have a different set of numeric characters. The character set Laura derived from the Delta C patent used 7 printable increments or units where 2 bars and 2 spaces would be printed. This yielded 20 combinations of characters, but there were 4 pairs that when read by Delta C rules yielded the same code for the pair. Since 16 characters were not enough, Laura tried adding 1 unit to the character set. This yielded 26 Delta C characters, which could provide the 2 sets of decimal characters, but it also added 14% to the width of the label and thereby the height. This would be a 30% increase in area, or a label of 1.7 euro x 1.03 euro. Laura felt this was not acceptable. He returned to the original character set with 20 characters, but 8 of those were 4 pairs with the same Delta C reading. He decided to use them all. To distinguish between the pairs, he would measure 1 bar width in each of the pairs to distinguish them from each other. For each pair, those bars would be 1 or 2 units wide. Laura did the Euro unregistered trademark T apply Bourmeister Euro unregistered trademark S equations to this set. He felt just 1 bar width measurement would not be too serious. As it turned out, it would have required over 50% increase in width and height for an area increase of more than double. Laura later admitted the 4 characters in each set was responsible for most of the scanner read errors. DeSaver, a mathematician, was given the task of proving the symbol could be printed and would meet the reliability requirements. It must be assumed he was unaware of Bourmeister Euro unregistered trademark S equations. He and Laura added 2 more digits to the 10 for error correction and detection. Then they decided to add odd-even parity to the number of units filled with bars in each side. Odd-even parity is a technique used to detect any odd number of bit errors in a bit stream. They decided to use odd on one half and even on the other. This would provide additional indication of which half ticket was being read. This meant that every bar width had to be read accurately to provide a good reading. It also meant every space would also be known. Requiring every bit width to be read precisely basically nullified the Delta C advantage except for the Delta C reference measurement. Only the strange character set and the size of the label remains as a shadow of the Delta C code. The size was still that calculated for pure Delta C. There are some fields of engineering that require little or no mathematical analysis since those fields have absolute components such as computer logic design. Most of IBM development was in this area. Mechanical engineering and electronic circuit design commonly require worst-case designs using known tolerances. Many engineers working with barcodes had little experience with such things and used somewhat intuitive methods. This was the cause of the poor performance of the Delta B code and quite likely the failure of RCAA unregistered trademark S Buller unregistered trademark SI scanner. Without Bourmestre unregistered trademark S breakthrough there probably would not have been an IBM proposal. As simple as it was, in hindsight no one else had found it. It might have been many years before a workable proposal would have been offered. Without Crozier unregistered trademark S Delta C barcode the proposal would probably have been abandoned since the label with Delta B was too large. Without Blora unregistered trademark S effort and persistence the proposal might never have been written. Whatever imperfections the label has, the improvement in print quality has overcome them to provide accurate scans most of the time. The following table shows the workable labels, available in the early 1970s, with their sizes. This is assuming a Buller unregistered trademark SI with the same information and reliable readability. See also, GS1 International Supply Chain Standards Organization, Proof of Purchase, References. US 3,832,686, Bilgot A, Ilan M, Barcode Font, published May 11, 1972, issued August 27, 1974, US 3,145,291, Brainerd, H.B., Identification System, published July 2, 1959, issued April 18, 1964 a railroad barcode. US 3,617,707, Shields, Charles B. and Roelif Stapelfelt, Automatic Car Identification System, published August 17, 1967, issued November 2, 1971 a, US 3,723,710, Krause, William G. and John E. Jones, Method and Device for Reading and Decoding a High-Density Self-Clocking Barcode, published June 28, 1971, issued March 27, 1973 a, external links, press release about 35th anniversary of Barcode, 25th anniversary review of UPC Impact, George J. Lannera's personal website extensive info from the inventor of the UPC barcode. Global Universal Product Code Database from GS1, UPC Search another free online UPC database with 5.6 million entries, EAN Search, History of Identification Codes, UPC EAN Check Digit Calculator, EAN MediaWiki Extension, a MediaWiki extension, visualizing UPC-A EAN codebar barcodes by specifying only the numbers symbols in the wiki text. ISO IEC 15420, International Standards specifying UPC-A, UPC and EAN codes fully.